There are two different types of supernova. One is called a type 1. Sometimes it is called a type 1a supernova. And these are white dwarf supernovas. The other type is called a type 2 supernova or a core collapse supernova. The one that we have been talking, and here's where it gets a little confusing. The one that we have been talking about so far have been core collapse supernovas. Now, so we're going to start with type 2, which is kind of contrary if you like doing things linearly. I am sorry, but this is how we're going to do this. A core collapse supernova, this is when you have a heavy star that goes supernova as a normal part of their life cycle. So you've got a normal star, probably starting with a blue star that's burning hot and fast. It switches from hydrogen fuel to helium fuel. It expands and it becomes a red supergiant. And when it becomes this red supergiant, it doesn't have enough heat to hold up its big bubble forever. And when the bubble collapses down, you have these massive heats and pressures inside the core, and that creates the explosion that produces a supernova. How do you tell one of these? Well, a couple things. One, hydrogen is still in the spectrum. The supernova that occurs, you still get some hydrogen that is left after this whole process. The core itself, we'll talk about what can occur with this core later. It can become exotic things like neutron stars, black holes, and pulsars, but we're going to talk about that at a later time. So this is one type of supernova, these core collapse supernovas. Typical life cycle event. The other one is called a type 1, sometimes called a type 1a, and sometimes called a white dwarf supernova. Yeah, I know it's confusing. Type 1, white dwarf, type 1a, yes, they are all the same thing. It's kind of like a Kleenex or a tissue. It's the same thing, kind of depends on who's talking. Now, a type 1a supernova does not have hydrogen left in the spectrum after the explosion. This is how we can tell the difference. Sometimes these are also referred to as a thermonuclear supernova. So it occurs from a different mechanical mechanism. And a type 1a supernova only occurs when you have a binary pair of stars, you have the red giant, you have a little white dwarf, there are those Roche lobes that kind of look like that. You've got a Lagrange point. And as this red giant expands and gets bigger and bigger and bigger, once it passes that Lagrange point, matter from the red giant starts to swirl into that white dwarf. Remember the analogy, throwing a paper plate on a dying bonfire. The only difference between a supernova and a nova is that the matter gets added very, very nutty fast, and the core of this star approaches that Chandrasekhar shear limit of 1.4 solar masses. So it has to do mostly with the mass of the core that is going to be the difference between a supernova and a regular nova. That's going to depend upon the mass of the actual core. So when this occurs nutty crazy fast, the star itself is going to go type 1a supernova or thermonuclear supernova. The core gets very, very hot very, very fast. So hot, so fast that the entire star explodes. It just gets blown to smithereens. And it just blows out in all sorts of directions. Any hydrogen that happens to be left, any hydrogen that happens to remain, due to this intensity of this explosion, the hydrogen and the hydrogen get fused to things like helium, and you end up with very little hydrogen left in the ending spectra. So there's no remnants behind. There's not a core that's left. There's no little white dwarf or anything left in the middle. The whole thing just gets totally blown to smithereens. When there is a type 1a supernova, these are nutty crazy bright. They can be as bright as 4 billion of our suns. This is a picture of a type 1a supernova. Beforehand, if you look up here, yeah, there's some dim stars in this distant galaxy, but all of a sudden, in a very short period of time, bam, you get this huge, massive, bright star that's actually brighter than the actual center of the galaxy. It's incredibly nutty bright. Why do we care so much about the type 1a supernovas? When we get in further chapters and we start talking about how do we calculate the age of the universe, one of the ways we do that is by looking at distances to far distant stars. If we want to calculate the distance to a distant galaxy, one of the things we've discovered is type 1a supernova are all very similar in their brightness. And if we can know the brightness of an object in space, we can use the inverse square law to determine distance. And so our understanding of everything we know about the cosmos, the age, etc., to a great extent depends upon these type 1a supernovas. They're very useful for finding distances to galaxies and things that are billions and billions of miles away. So one more time, because this can get confusing, the two types of supernova. The type 2, this is the core collapse supernova, and normal life cycle goes from burning hydrogen to burning helium. It expands, it collapses, the core rebounds, and you get this shock wave, and there is a little core that's going to be left. That is typical life cycle of a big star. Type 1a supernova, very different mechanism, always occurs in binary systems. You're going to have a red giant and a white dwarf, the Roche limit. As the red giant expands, it's going to dump some matter into that white dwarf, and it's going to detonate an explosion that will blow the star into smithereens, and there is nothing left in the core. How common are supernova? There are only 3 visible with the naked eye that have been seen in the Milky Way in the last 1,000 years. So the quick answer is they are very, very rare. We do not see supernova often. So 3 in the last 10,000 years is not many. The most famous of which is Kepler, Johannes Kepler, that you remember from our discussion of the history of astronomy. He saw a supernova in 1604. There have none that have occurred in the Milky Way since the invention of the modern telescope. When will one pop? It can pop any minute. Seriously, any minute. Now, fortunately, that is within the Milky Way. Astronomers have seen lots of these in other galaxies beyond our Milky Way galaxy. That's why we know so much about them. But there is no supernova that has erupted anywhere nearby in a long time. Is that a good thing? That can be a good thing, because depending upon how close to us something goes supernova, it could cause a lot of grief and havoc here on planet Earth. We just don't know. We just don't know until it happens. This is a Spitzer Space Telescope of Kepler's supernova from 1604, supernova 1604, and it's been exploding for the last over 400 years, and this is what it actually looks like today. Isn't that cool? All right, that will end our discussion of supernovas. Next time, neutron stars and pulsars. See you then.